Hi everyone, welcome back to the workshop, and it's repair time again. And I have to admit right off the bat, I have so been looking forward to this unit arriving. It's a Keithley 2001 multimeter. It's a 7.5 digit multimeter. And they don't come up very often. I spotted this one for sale. It's just arrived in the workshop today, and I can't wait to get inside it and to have a look around and see what sort of condition it's in. Let's get it down onto the workbench here, and let's get the cover off and let's take a look inside. It looks pretty clean inside. Of course, it does have this cover, so we'll need to get that removed and take a look underneath. And on the other side, you got the CPU board. Again, very clean. So here we are for a good look inside at the analog board. I was just having a little browse around and I've spotted something already. So over here we've got the A to D converter board. So I'm just going to remove that because I've spotted something underneath that I think requires a little bit of a look. Let's get it out. And I think it just unplugs. There we go. So that's the A to D converter board, I believe. And look down here. Let me zoom in on that. Somebody has had a go at trying to replace or resolder an LM339. That's a quad comparator. Wow, what a mess. Hopefully there's no traces on the board being lifted, but yeah, I think I'll pull that from the board for sure and replace it with a new one and have a good inspection of the traces in and around that comparator. And the other thing I've spotted whilst I'm down here is that we've got a few test points there for, looks like, the plus and minus 8 volt, plus and minus 15 volt and plus 5 volt supplies, probably for this particular part of the circuit for to do with the A to D converter. Okay, let's tear it down. Let's get the circuit boards out. Wow, basically you have to take the whole thing apart. Remove the transformer, remove guides, remove the push rods for all the buttons in the front, remove the display assembly here. You basically have to tear it completely apart. And I've actually received all the capacitors and the LM339s that I need, even the fuse holders here, the new ones. I can replace them as well. So I'll get going with that, and I'll start replacing the caps, and then I'll come back when we're ready to reassemble, or if I find anything in between times. Okay, with the digital board disassembled, something caught my eye, and that is this 5 volt regulator here is completely discoloured. That's not looking good. So let's put the meter on it and see what we've got. I think that's the output. Wow, dead short. Oops. And the input, 8 ohms. That's not looking good. That's not looking good at all. So I'm going to remove that from the board. I'll not put a new one in just yet. I'll remove it from the board and do some more measuring. So let's go across it first. On the output, it's not shorted. Input's 8 ohms, so that's definitely too low. That's the ground. And on the circuit board, go across the output, we've still got a dead short, but the input's up. Yeah, it's charging a capacitor, so that's fine. So we've got a dead short on the digital board somewhere. Oops. Let's dig a bit deeper. Well, this repair is going to turn into a cracker, I think. I think we've got problems, big problems with the digital board. Brilliant. So I've been doing some digging around. I've been putting my ohmmeter in 6.5 digit mode, as high a resolution as I can possibly get, trying to narrow down which section of the board had the lowest resistance. I've done that in a video before, so I'm not going to do it again here. And I kind of got two areas, I think. It was real confusing. I was getting low readouts at both ends of the board, maybe not so much in the middle or around a certain area, so it kind of got me to thinking there was a short circuit in two areas. So I narrowed it down to one of them anyway. There's two diodes here, CR618 and CR617, and those are a couple of protection diodes there, which are absolutely dead short, both of them. And basically, as far as I can see, there's a digital line coming in via this connector here that goes away off to this IC over here, and those were dead short. So I cleared that, and my dead short, which was down about 0.06 of an ohm, is now 1 ohm. So it took a definite jump north. So there's still a short circuit somewhere, and I really wasn't getting anywhere with the meter. It was kind of giving inconsistent results. So I've resorted to a different way of doing it, and that is to put 5 volts into the board where the regulator is, and use the constant current mode of my power supply, starting at basically 0 milliamps, and start going up in steps of 100 milliamps until I could see on the thermal camera whereabout I was getting the hotspots. Now I was getting 2 hotspots, the CPU itself, but also this IC over here. So just to demonstrate, here's a thermal camera, and you can see the CPU down here. It's got a hotspot. There is some other hotspots like this one over here. That's a reflection. That's just the copper pad that's shining there, and it gives a false impression of a high temperature on the thermal camera. But if you look across here, actually we've got 2 hotspots. We've got this IC here, the one I was talking about, and we may have this one here as well. So we're getting somewhere. I've removed this UDN2596. It's just a driver chip, a buffer driver, and now my resistance across the 5 volt supply, it's creeping up. We were at 1 ohm, and now we're at just under 6 ohms, so it is creeping up. And I have put 5 volt across it, current limited, and it's still drawing far too much. So I think the next one along is this TK7487. Now I can't get them anymore, but I can get a compatible chip. But I'll remove it from the board, and then we'll see what like the resistance across the 5 volt supply is like after that. Only other thing that was getting warm, as you could say, as you saw in the thermal camera, was the CPU itself. Okay, I think I've just got one short circuit left. I have removed the TK7487, put a socket in its place. I've removed the UDN2596A socket there as well. And I've been going over the 5 volt supply across the remaining chips, etc. on the board. And I think I've got one short circuit left. And I believe it's the actual CPU itself. Now there's 2 clues for that, and that is, if I turn the board over, you can see that there are a bunch of capacitors dotted around on the back of the board. Those are the decoupling capacitors next to the various ICs and connectors. And as you can see, the CPU here actually has 4 of them, because there are multiple supply pins to that CPU. There's not just the one pin, and I've gone over each one of them and narrowed down the lowest resistance across C640. If you look down here, we've got the CPU and we've got the crystal, and if I find a ground, which is actually the body of the crystal, it's grounded, it's soldered down at the back there to the circuit board. If I just use that as a ground and go into each one of the pins on the crystal, you can see that this leg here you're talking 0.6 of a mega ohm, and if I go into this one here, 3 ohms. Now let's take a look at the circuit diagram. Here's the actual crystal with its parallel resistor there and the two 33 picofarad capacitors in the back, and you can see it's interfaced directly to the CPU, and that 3 ohm resistance that I'm getting is on this EXTAL. That's the crystal input, or the external clock input, and there's no way that should have a 3 ohm resistance down to ground in any circumstances. If you're not using a crystal, you can actually drive that. It's CMOS compatible, that input, if you're driving the CPU from an external clock source, so there's no way it should have that resistance there. So I believe it's internally shorted. So all in all, I think the CPU's got to come out. Now this is a QFP 132. It's a 132 pin package. This is an adapter for my heat gun here, which sits very nicely completely over the package. The little gaps at the side here actually straddle the plastic parts of the package there, so that it goes really nice and tight down onto the top of that chip. So let me get going. Let's get that package off the board there and clean up the PCB and see where we are after that. There we go, and that's it off the board. And as you can see, every pin nice and intact, no pads lifted. Here we go, across the 5V supply, 29.76 ohms. We're getting closer, but we've still got some problems on this board. Right, I think I've found the next problem, and that is the actual 4 megahertz oscillator itself. So I'm not going to remove it from the board, I'm just going to desolder it at the supply side, just lifting it very slightly from the board to isolate that supply pin there. It looks like an IC, it's got the same sort of pin out. A pin 2's your ground round here, and pin 4 is your supply pin. And if I go across the supply pin now on the actual chip itself, I'm getting 84.5 ohms. So with it lifted, the actual oscillator itself has got about 85 ohms across it, and with it isolated from the board, I'm now getting about 45 ohms across the 5V supply on this board. Still too low, I think, so we need to keep going and find the next culprit. In the meantime, I'll desolder that completely from the board because I think it's gone. That's the crystal down here, so don't worry about that one. And we've got the tops of 2 capacitors here, but over here we've got a hotspot, and there looks to be 2 FETs on that board, and they are getting hot. Let's take a look at that. Okay, I've removed this little daughter board from the board and powered up the main board again. 30 milliamps at 5 volts. That's much more like it. So it looks like this on its own was drawing about 200 odd milliamps. So yep, this has also got a problem. Now what is it? Well, let's take a look at the schematic. It took me a while to find it on the schematic because none of the actual components on it are actually detailed. This is it here, known as U625. It interfaces to the actual display board, and what I think it's probably doing, it's probably producing the high voltage supply for the actual display board itself, and it's probably got a little oscillator or something like that, and then step up the voltage using this little coil here to produce that high voltage. Okay, I've reverse engineered this little board here because I don't have a schematic for it, and I really needed to work out how it was working in order to troubleshoot it. So if we go down onto my little reverse engineering drawings here, this is what I started with. I basically drew the components out as they lay out on the board. Then the red pen is just the tracks on the board. I'm interconnecting it, and then I transferred this to a small schematic. And if we look at the schematic, starting with this side over here, I think this is the final high voltage output that goes off to the display. And the reason I think that is you've got an electrolytic capacitor here, this one here, it's a 250 volt 1 microfarad electrolytic capacitor with a bleed resistor across it. It's connected to a bridge rectifier and one of the coils on the transformer, one of the output windings. So I think this is your final output here. On the other side, we've got 2 transistors, 2 NPN transistors, 2 diodes, etc. and a 5 volt supply coming in here on a center tap of this winding here. And either side of that winding is connected to the collector of these 2 transistors. I think these are switching on the primary side in order to generate a secondary side. And here we go, I've got the 2 transistors off. They're just general purpose power transistors, small ones. And between the base and the emitter, 0.6 of an ohm and 160 ohms between the base and the collector on that one. So that one's gone. And a similar story here by the looks of it. Just reverse the leads. Yeah, 0.4. Yep, those 2 transistors are gone. Okay, next thing I'm going to do is put the board back together again. I've got quite a lot of parts in a box here, stuff I'd received, so I'm just going to go way off camera and repopulate the board. Some of the ICs I'll be putting back on that I'd taken off and they're apparently okay, and some of them are new stock that I've managed to pick up. So I'll go away and put the board back together again. Okay, so the chip I was waiting on coming in finally fitted, and that was the dual channel supervisor IC. So I've got everything fitted that I think I need to get fitted at the moment in order just to get the CPU up and running. And here is the supervisor IC itself, and you can see basically it just monitors the 5 volt supply and it just ties into the reset pin and also the halt pin on the actual CPU. So I'd expect to see both of those lines high when the microprocessor's powered up because they're both active low. So let me reposition the camera, let me get the scope hooked up, and we'll monitor those 2 lines there. Right, the board is actually powered up, so I'll just go on to the reset line there, and yes, it's high, well, kind of, nearly just under 3 volts. So I'll just adjust the power. I'll just adjust the 5 volts down quite a bit. There you go, and you can see it flipped low there because I'm only at 4.3 volts. Now I'll just increase it back up to 5 again, and yes, it looks like the reset's working okay. So I'll go on to the halt line whilst I'm here. That's this one here, and that one's permanently low. That's not good. So let me just adjust it, turn the power off. There we go, and back on again. Let's see if it flips at all. And it doesn't. That means that the microprocessor is permanently in a halt condition. And I can probably verify that if I go into the bus somewhere on the RAM. High, high, high. Yeah, that CPU is not running at all. Okay, so what am I going to do about that? Well, I've got a little bit of a theory, and that is I'm wondering whether these 2 proms here are actually blown as well. The 5 volt supply going haywire, it's probably took them out as well, although they're not hot or anything like that. Now I did kind of anticipate this, like I said, so I actually did order 2 replacement proms, 2 AT27C040s. because the schematic diagram does actually mention that there are 27C040s fitted, and these are readily available. So I've bought a couple. They're one time only. They're not EPROMs, they're PROMs, so they're one time only programmable. And let's go and program these two up, and we'll take it from there. So there we go. I've got the two new PROMs here all ready to go, and I've marked them odd and even, and as you can see, it's B17 firmware version as a bit of a bonus there to the B16 I've got currently fitted. I was able to find on the XDev site the bin files for the B17 version. So let me go and plug these onto the board, and then we'll power up again and we'll see what happens then. And there we go, two new PROMs fitted. So let me just position the board ready for another power up, and we'll take it from there again. So I've got the scope all ready, so let me just put power on, and we'll go down onto the reset pin again first of all, and that's high, that's good, and the halt pin is also high, excellent. So let's go down onto the bus on the RAM here, and let's see what it's doing. Ah, look at that! We've got something. And that's unmistakably like a data bus or an address bus that's just running away rather nicely, and just scoping various random pins there. That's looking good. I think the CPU's up and running no problem. Now the CPU does have a built-in watchdog, a software watchdog, and if the program crashes or it comes across any problem, it will do a self-reset. So going back onto the reset pin again, it looks like it's permanently high there, so I would assume that the program is just running away perfectly. No problem. Now the next thing that I want to do, I really want to plug in the display and see if we get anything on it when I power up the main processor there, the main digital board. And I have actually gone ahead and measured across the various caps, and I've not got any short or anything like that on the display board. So whether it survived, I don't know. It does have its own microprocessor, so I hope we don't have to buy a new one of them and reprogram them, not to mention replace any of the other chips. So here's hoping that this works, and this basically just plugs straight onto the digital board. I got two new transistors. I actually replaced them with the exact type of transistor that was on it before, the 2N6715 I believe it was. So I believe this is ready to go back onto the main digital board, and I should be able to measure the high voltage connection there and see what it's doing. So I've got the board soldered in now, so let's put the meter on it and see if we're getting our 60 volts. So there's the, just put power on now, and we're getting 58.3 volts. Perfect. And I think we're ready to go. I have actually verified that I'm getting a 4 megahertz clock from the new Epson oscillator I'd fitted here, which basically just goes direct to the header for the display board, and it's present, so there's no problem there. I've got my 60 volts, got my 5 volts through the board onto the header as well. I'll increase the bench power supply, and let's see if we can get 5 volts into the system now. So the power supply is off camera, so I'll just adjust that up and see what happens. Yeah, we're up about 4.6 volts at half an amp there. And there's 5 volts now. No, it's dropped down to 600 milliamps now. No, I don't think that's right. It's too much current consumption there. It's only a 1 amp regulator that's fitted, so something's not right. This display board's drawing far too much power. So certainly no dead shorts, so I think I'm about ready to try this board on my original digital board. Okay, let's go for a power up off camera here. And 5 volts is on. Yes! model 2001 Rev B17, which is exactly what I installed. Error code 511, GPIB address lost. My CPU's up and running. Perfect. Okay, the next thing I want to do, I do actually want to fit in the TechMOS IC that I removed from this socket here. I don't know if this chip's working, but what I want to do is actually just see if it actually powers up and the current doesn't go sky high. I just make sure I can power up. I do have probably one that I can rob off of this digital board here. This is actually an EEPROM, so I think this is a microcontroller if I remember rightly in its own right, so it's got code in it. It's not code that's transferred from the main CPU. I think it's actually burned with code directly itself, so whether this one's been wiped by that 5-volt supply, I don't know. I think it probably has. So yeah, worst comes to the worst, I'll remove this one from the board and we'll use it. And probably the same with the GPIB controller IC. That's just a standard IC and I should be able to use it directly. So let me go and fit this TechMOS and we'll try another power up. Well, that was a fail. It went straight to my 600 milliamp limit there, so that IC is probably gone. So I'll remove the other one from the other board. And there we go, that's the IC removed, and whilst I was at it I just desoldered the GPIB controller IC as well. So next thing to do is to clean up the pins in this one here because it's going into a socket now, and I'll just leave the GPIB controller IC for the time being, but it's there if I need it. Not exactly a tight fit, might have to play with the legs a little. And let's power that up and see what sort of consumption I'm getting now. Just under the 600 and no more. Okay, we'll call that a win for the moment. I think next thing I'm going to do is I'm going to turn to the GPIB controller IC. But first of all, let's take a look and see if we're getting a GPIB address on the actual display. So, sorry I can't turn this round, but it's the best I can do at the moment. Let me just power it up again. Address 16, but then it disappears. It comes up GPIB address lost. Well, I've just scanned GPIB network using my little remote 82357B, and it's not finding it. And I did confirm that I was able to find some of my other devices, no problem. So I don't think GPIB is working. Now, of course, it could be the buffer ICs here, or it could actually be the GPIB controller. So what I think I will do is I'll try replacing the controller first. Well, that's the GPIB controller IC removed from the donor board, and I've fitted a socket to my digital board here. I had to file down the side of the socket, the new one, just for the tiniest of fractions, not even half a pad of the ICs, just to move the socket just that way, just a very slightly. So I've done that and it's soldered up in place. I've got the new controller chip which I can go ahead and fit now. So today I'm going to start taking a look at the analog board. We're going to get the meter down onto it and let's check for short circuits, etc. If you remember in the part 1 video, I did actually notice a problem up on the top left hand corner here where an LM339 appeared to have some problems. So I'd actually pulled that from the board just ahead of going over the board with the meter, checking for shorts, etc. So we'll get on with that today. Now, good thing is I do actually have the donor board here, so any parts that I do need, hopefully I should be able to lift from here and put onto this board here. Okay, so here's the power supply circuit and the primary side of the transformer. Down at the bottom left here you've got the mains switch. It's a hard switch, and you've got the AC live and the AC neutral. And straight away, if you follow up the AC live, you'll see it doesn't go to the primary side of the transformer directly, which is over here. It goes onto one of the AC sides of a bridge rectifier. The other side of the bridge rectifier, the other AC side, actually comes down here, goes away through some relays, more about that in a minute, and then into one side of the primary side of this transformer. The other side of that primary side then comes back to the neutral side. So effectively, the bridge rectifier here is in series with the primary winding of the transformer. How can that work? Well, Marco Reps did a Keithley 2001 repair on his channel, and his little gem of information regarding this resistor here and this FET here gave me the information that I needed in order to work out how this was working. So your live comes up here, your AC live comes up here and into one of the AC inputs on that bridge rectifier, as I mentioned. Now if you imagine that none of these components here are fitted, there's no MOSFET, there's no resistor or anything connected to the positive and negatives of that bridge rectifier, then when the AC comes up on here, the positive side is going to conduct onto this through this diode here and just stop there. It's not going to go any further. The negative side is going to conduct and it's going to stop at this point here as well. Nothing's going to happen. You're certainly not going to get anything coming down and along towards the primary side of that transformer. However, this resistor is the key. So you can see that this resistor here basically connects between the positive side and back onto the negative side. So with that connected, you can imagine your AC current's coming up through here. It conducts down through here, the positive side, goes away through this resistor and back and down through this diode and then onwards towards the primary side of the transformer, and basically the opposite side for the negative going voltages. This 470 ohm resistor is basically your bootstrap resistor. It gives just enough current to flow in order to get the transformer working and to produce some sort of secondary voltages, at which point a control mechanism starts up. And this is where the MOSFET and this photocoupler come into action. So there's a control signal that comes up here through this photocoupler and onto the gate of this MOSFET. The amount of current that flows through the MOSFET is controlled in order to regulate the primary side current and therefore the secondary side current. Now we also have some relays here that I mentioned earlier. Basically one of them takes care of the 220 110 volt selection, basically selecting different taps on that primary winding, and you've also got a high-low control relay here and here, and I think that's just used to enable in the extra turns required going from, for instance, 220 to 240 volts. So how does this 220 volt 110 volt operation work? Well, the relay here, the main relay involved, is driven from positive relay 1 and the other side of the coil is actually grounded. So let's take a look at where this signal comes from. And here it is over here. And what you've got is another secondary winding coming into a bridge rectifier. You've basically got an LM317 producing an 8 volt supply and a MOSFET here basically controlled by a comparator. One side of the comparator here, the positive side, is basically two resistors, a voltage divider, so you've got 4 volts at the positive input of that comparator. The negative side of the comparator basically comes from ACL. ACL was on the first schematic I showed you. That was your AC live. That's your 240 volts live connection. So you've got a large dropper resistor here and a bit of rectification, a smoothing capacitor here, and I'm presuming at pin 3 you're going to get more than 4 volts when you're using 240 volts, and it'll go below 4 volts when it's set to 110 volt input. Therefore, the output of the comparator is basically going to turn this MOSFET off and on. Therefore, the relay is turned off and on. So back to the first diagram, here's that 220, 110 volt relay, and you can imagine if there's some problem with the signal here coming from that other schematic driving this relay, or if there's a problem with the relay itself, you could theoretically have 240 volts coming through on the 110 volt side of this primary winding here, and basically over voltaging the secondary side, which would in turn over voltage all of these regulators here, the positive and minus 15 and the plus 5 volt regulator and these unregulated supplies. They would all just go haywire. So I probably think that's what's happened in this case. So for the testing of the analog board, I'm certainly not going to hook up the transformer. What I'm going to do is I'm going to inject my own voltages here. I'm probably going to inject plus 15, minus 15 volt directly, because the regulators are removed at the moment, and that way I can have good control over the DC voltages powering the analog board. And then later on down the line, what I can do is I can probably disconnect the secondaries on the transformer and make sure quite separately that this primary side is all working. I can simulate this control signal coming up here, and that way I make as safe and as good a test as I can with the circuits involved. Okay, so let's start probing the board. So the first thing I'm going to need is a good 0 volts. And these are the plus and minus 15 volt regulators. This one here being the positive 15 volt, the 7815. So the tab of it is 0 volts. And I think this is probably 0 volts here as well. Yeah, okay, but we'll go with the regulator to start with. So at the left hand side of the board there are some test points here. Plus and minus VF, minus 15, positive 15 and plus 5. So let me just go down looking for shorts. So the minus 15 one is showing about 20 ohms. The positive 15 about the same, and about 25 ohms for the plus 5 volt. Well, none of them seem right. Certainly the minus 15, plus 15 and plus 5, they all seem too low. So I think we've got some shorts. I have actually decided to change tact a little bit. I was planning and trying to get the original board up and running. Yes, it looks a little bit like a lot of the ICs are short circuit. It looks like that power supply failure has probably zapped just about every IC on the board. But I do have the donor board, which I originally didn't want to use because it's an older board and it looks a little bit tatty. Someone's already had a go at it by removing the electrolytic capacitors, etc. And I really didn't want to use it. However, on review of where this board came from, it came from a country that doesn't use 220 or 240 volts. They're down at 100 volts. So even if the pre-regulator part here, which I had some concerns of, which I mentioned in the last video, it looks a little bit burnt deposits in and around it. Even if that did fail, it wouldn't have put a higher voltage through onto the secondaries. There would have been no over voltage onto the secondaries. So I'm probably in a good position in regarding everything downstream of the actual regulators. So I think I'm going to go ahead and start working on this donor board and using it. So taking a closer look at the donor board, I have actually measured across some of the digital ICs, across some of the DC supplies, the plus and minus 15 and the plus 5, and they look in great condition. Possibly one of the rails isn't, but when I turn the board over, you will notice, let me zoom in a second. that across the minus 15 volt rail you've got this tantalum capacitor which is clearly gone, so maybe that'll sort out the 15 volt rail, I'm not sure. There's also some residue, I don't know if you can see that on the camera there, and that looks like leakage from electrolytic capacitors. How it's ended up in a line right along there, I'm not really sure. And also the same down here. So what I'm going to go ahead and do is I'm going to remove these electrolytic capacitors. I'm going to move the two 15 volt regulators and the 5 volt regulators. I'll put in new ones of them. I've got a bridge rectifier here that's hanging out of its holes in the PCB. Somebody's had a go at desoldering that. And more importantly, the pre-regulator circuit here, I'm going to start removing the components that I don't need, and the automatic 110 240 volt selection, I'm just going to bypass that completely. Okay, I've removed a heap of components and here's my little collection here. And the first thing was the electrolytic capacitors here. Yeah, they're wet underneath, so yeah, they've been leaking. Luckily, no damage to the PCB at all, although it's quite wet, so I will need to get that cleaned up. I've also gone ahead and removed quite a lot of components from that main switching circuit there. And I've removed the regulators there. So the next thing I'm going to do, I'm actually going to clean up the board now. Yep, I've got those leaky caps there, but if you take a look over here, so you can see there's quite a lot of dirt in and around those components there. That's not blast damage from a blown IC, that's dirt. And I think it's no coincidence because it's right next to the fan at the back of the unit. So as it was pulling air down across this part of the board here, it's probably taking rubbish and dust and everything from the outside and depositing it right across the board there and out the fan, and some of that dust has found its way underneath some of those ICs. And in fact, some of those tracks here have a line of residue attached to the top of the track. It almost looks like the track is vaporized, but I don't think that's the case. I just think it's dust attached itself to those tracks when, you know, when power was in it. It's maybe attracting the dust, that fine layer of dust, and you can see that fine layer of dust as well in and around here as well. So I'll get the ultrasonic cleaner out and I think I'll give this board a good old clean. And there's the board completely cleaned off and totally dried, and it's made quite a difference. Especially around this area up here where all that dirty marks were, there's still a little bit of staining on the PCB, but nothing like it was, and everything's totally dried off and ready for testing again. Okay, and moving on, I've done a little bit more work and I've been preparing the board for first power up. I've fitted all the new capacitors there. There's one over here that I don't need because that's on the pre-regulator 220 110 volt selection, and that's all been removed, as you can see. I've also been cabling up the DC supplies here, bypassing the regulators. So I've got my plus and minus 15 volt here and my plus 5 volt, and it's a shared common between the three rails, so that's fine. And the BNCs over the right hand side here, that's off of my board as well, just purely because the ones off this donor board were all tarnished and probably a little bit corroded inside, so I wanted to use the nice shiny ones. Everything else seems okay. I did inspect underneath the capacitors before I fitted them, and there's no broken tracks, and the corrosion from the leaky capacitors didn't seem that bad. It just slightly marked the top of the PCB there, but hadn't actually damaged any of the tracks. I'm going to use my BB3 power supply. It's my go-to power supply on the bench here for things like powering up boards for the first time, because I've got good control over the 4 channels in the board here. I'm just going to be using the 3. I've got the channel 3 is going to be used for the 5 volts, and channel 1 and 2 I've hooked up for my plus and minus 15 volts, as you can see here with the cables here. The one interesting feature on this power supply is that it does have some digital inputs on the front panel here, and I've managed to wire up a couple of switches there, and these are user configurable. You can put scripts on an SD card in the front here and write them for all sorts of things to run Skippy commands, etc. on the power supply. So I've gone ahead and written a script in order to make use of those 2 buttons, and if I just load up the script, I'll show you what it does. Go to the file manager, into scripts, and I've got an on-off script that I've written there. So that's it running, and basically if I just hit this switch here, all channels go off. Hit the other switch, all channels go on. And the idea behind that is I can put this switch nice and close to where I'm working, so that if ever any of the channels in the power supply suddenly start running away by some problem on the board, I just need to hit this button, emergency stop in other words, and it'll turn all the channels off. So we're all ready to go. I've got it all cabled up, we're all ready to power up. I've set the plus 15 volt rail to 200 milliamps max, the minus 15 to 200 milliamps, and the plus 5 volt to 300 milliamps. I've got no idea what sort of power this board's going to draw, but those are quite low settings there, and it should highlight any problem if there is one. So all I've got to do now is hit the button, which I'll do off camera, and we'll see what happens. Okay, go. Okay, and we've got plus and minus 15, 150 milliamps for plus and minus 15 volt rail, and we're pulling less than 250 milliamps on the 5 volt rail, so it's got power. So power is on. So I'll go over the test points at the left hand side of the board here. Starting with a plus 5 volt, I should get some volt drop across all these long cables, but we'll see how it goes. 4.9 volts for the 5 volts, 14.9 for the plus 15, and minus 14.2 for the minus 15. And yep, minus 5 volts, spot on. And just for fun, how about the voltage reference from the LM399? Well, that's on pin 6 of this IC here, I think. So 3, 4, 5, 6. Should be about 7 volts. Oh, it's not. 1.8. Wow. Okay, after a little bit of digging, looks like I won't get the voltage reference until I've got the digital board connected. There's a bit of logic behind that as far as I can see. It needs some commands to switch on some transistors in order to enable that. So that can wait. And so far so good. Okay, and back to the pre-regulator circuit here. You can see that I've cleaned up the board, especially underneath those ICs, etc., where I've managed to use my fiberglass pencil and just clean up the area underneath those ICs as best as I can. And it doesn't look like at the moment there's any broken tracks or any corroded tracks, so I should be in good shape. Now, of course, I won't be fitting the relays. I will be bypassing them with links. That shouldn't be a problem, but I will need to refit the components that are actually used for the pre-regulator, like the MOSFET, the bridge rectifier, and the resistor, etc. Now, you could be asking, why not bypass the pre-regulator as well? Well, I think there's a good reason for that, and I did do some testing and I did look at doing that. Let's look at the schematic. Here is the pre-regulator circuit itself, and you can see there's the MOSFET and that 470 ohm resistor that I explained how that worked previously. So what I went ahead and did was I took the transformer and I just hooked up 240 volts to it across the outer windings there, and measured the AC outputs on the secondary just to see what I was getting. And the reason I was doing that is I wanted to see that in normal operating mode, is that MOSFET completely switched on, and therefore effectively short-circuiting the positive and negatives on that bridge rectifier. If that was the case, then I could probably do away with the pre-regulator and just wire up 240 volts across the primary and off we go. Well, looking at the outputs that I was measuring on the secondary with 240 volts going in, they're all too high, which leads me to believe that MOSFET is never switched on fully. It's always limiting the current along with that resistor. And I think I've worked it out that in order to get the secondary voltages that I think would be necessary on the output of the transformer, I'd be looking at somewhere around 170 to 180 volts across that primary circuit there. And obviously, putting 240 in there, that's not going to work. So I'll definitely need to go ahead and put the pre-regulator components back on the board and get it operational. Now, I've not got too much of a problem with doing that because the pre-regulator can only ever reduce that 240 volts down. It can't step it up. And there's the components I need fitted for the pre-regulator. In fact, some of the pre-regulator circuitry is actually on the digital board, so we'll take a look at that in a second. But this is all I need on the main analog board. You've got the connector here for the secondaries. You've got the main photocoupler with the MOSFET and the big 470 ohm resistor, power switch, mains AC input, the bridge rectifier on that input, and the fuse obviously. And I've also linked out the relays so that I'm basically selecting the 220 or 240 volt tap on that transformer there on the secondaries there. All this other circuitry I don't need. So let's take a look at the schematic and see why I don't need those parts. And here's the photocoupler and the MOSFET and the big 470 ohm resistor. All these parts here are to do with the high-low selection, the 220, 110 volt selection, so I don't need any of them. Some of them are left on the board. I don't see any harm with that at all. I'll probably lift R123 and R250 just to stop this part of the circuit here getting any power. And of course, these three relay contacts here, I've jumpered so that I'm basically getting 240 across the outer taps of that primary side of the transformer. So this is the high-low control, the 110 volt, 220 volt selection, and the high-low control. I don't need any of this. There's that LM311, the LM317 producing that 8 volt supply, the 555, the optocouplers. None of that's needed at all from what I can see, because ultimately all it's doing is driving relay 1 for the 220 110 volt control and also relay 2 for the high-low control. I'm gearing towards powering up, but I'm trying to test all the individual parts of the pre-regulator circuit, and what I would like to test is this control signal here that controls this optocoupler, which controls the MOSFET here. I need to know where this is coming from and how it's working and try and make sure it's okay. This signal here, cont, comes from the digital board. Let's take a look at that. And here's the digital board. Please excuse the annotations, it's just to keep me clear as to how this thing works. So what you've got is secondary coming in here from a transformer, a bridge rectifier, there's that large capacitor on the digital board. You've got a voltage doubler circuit here which is feeding a 5 volt regulator, providing 5 volt for the integrator and a comparator on this part of the circuit. Now, fed off of that unregulated supply from the output of the bridge rectifier is a voltage divider, divide by 3, and that basically feeds one of the inputs on this integrator. The other input on the integrator is basically the 5 volt supply divided by 2 because you've got a voltage divider here. And so basically the integrator is monitoring the voltage across this large capacitor, this unregulated DC here. And as it goes up and down, it can turn off this FET here, which basically turns on and off the control signal. So I can simulate this. I've not hooked up the AC yet, but I put in an unregulated supply coming in here, and I can vary that up and down, obviously giving it enough to provide 5-volt regulation, and I can vary that up and down, therefore varying this signal here going away off to the integrator. And if I wind the voltage up, I should be able to see this FET switching. And so here's the digital board, and I've just hooked up an LED, a series resistor and an LED to that control output, i.e. the output from that FET, which is down here. And I should be able to vary this supply, this DC supply here, coming into this large capacitor here. I should be able to vary up and down and watch that LED go off and on. Now, why use an integrator? There's the actual integrator IC there. Why use an integrator? Well, if you just used an op-amp or something like that, then it would switch too fast. You'd end up getting a chattering on that control output as noise on this unregulated DC supply went up and down. It would end up causing this control signal to chatter. So by using an integrator with a large capacitor, which is down here, then you're able to slow down the operation of that output from the integrator. I'll try and demonstrate that now. So I've got my power supply hooked up. I've got it set for about 7 volts at the moment, and it's enough to provide a 5-volt supply for that part of the circuit. And if I wind it up to something like 11 volts, I think I managed to get to, and you should see this LED turn off. And then as I wind it back down again, it will come back on. So just let me put on the power supply off camera. And there it is. You can see the LED is on, and I'm set for 7 volts. So I've got power to the digital board. And if I just wind that up now to 11 volts, you see the LEDs going off and then back down again to 7 volts. The LEDs come back on. So I know that this circuit's working now. So I hadn't replaced any of the ICs on this part of the circuit, and I did actually want to test it to make sure that control signal's working before I hooked it up to the analog board and obviously the transformer. But it seems to be working great. Well, we're getting pretty close. I think I'm ready for a full-blown hookup. All I've got to do is fit the 5-volt and 15-volt regulators to the analog board here. I've got the small heat sinks all ready, digital board's ready, the display's ready, and the transformer sitting here as well. So I should be able to power up on the workbench like this. As you can see, you've got the AC input coming along here. The easiest way to hook this up to the board was just to use the inline line filter that came with the K2001. It's just got the right header on it and everything. I've got the heatsink down there on a temporary heatsink on the big resistor, the 470 ohm resistor, and that MOSFET on the pre-regulator there. And as you can see, here is the primary to the transformer hooked up here. I've just got a couple of multimeter probes across the winding that we're powering at 240 volts just so I can monitor that. I've got the secondary coming in here. I've also got the digital board hooked up. As you can see, you've got the small ribbon cable. It's probably just out of sight actually. Small ribbon cable connecting it to the digital board. I'm monitoring the 5-volt supply on that digital board just on this meter over here, just so I can see what's going on. And I've actually got a heatsink on that 5-volt regulator on the digital board just to mimic the bottom plate underneath the digital board that regulator's bolted to. So multimeters at the back. I've got the AC input coming from a variable transformer. I've got the AC voltage across the transformer primary just so that I can see what's going on. If the pre-regulator's working, I should see this voltage here being slightly less than the AC input. I'm also measuring a positive BS supply. There is actually an unregulated DC supply from the secondary on the transformer. It actually goes through a little voltage doubler, and on the schematic diagram it does actually say it should be between 34 and 38 volts, something like that. So I just thought, because it's something I've never monitored previously. I've never tested previously because I've never hooked up that secondary. I just thought it was worth monitoring that. And this meter at the end here is just across the 5V supply on the digital board. So what I'm going to do, I've got my variable transformer hooked up. I'm just going to wind the voltage up slowly so that I can keep an eye on the various supplies. I'm not just going to whack in 240 volts and hope for the best. So let's go. Okay, let's just get power going. And I'll just wind it up reasonably slowly. There we go. Now it's 60 and 60 volts there. BS is at 7.5. And you can see the 5V regulator starting to work now. We're at 113 volts on both, 16 volts and 2.7. It's coming up. And we're at 200 volts. We've got 5 volts on the digital board. BS is at 33 volts. That's good. We're now at 240 volts input, and very crucially, the transformer primary is at 220. Looks like that pre-regulator's working, and the positive VS is at 36 volts. It's perfect, right smack in the middle of the range there, and I've got 5 volts on the digital board. Everything's looking good so far. So I'll turn off the power now. And what I'm going to do now is been on for a few seconds. I just want to go around everything, make sure all the heat sinks are okay, they're not burning hot or anything like that. Resistor on the pre-regulator is just starting to get a little bit warm, very, very slightly, just above ambient temperature there. And nothing is hot at all. This 5V regulator down here, very, very slightly warm. That's to be expected. Everything's perfect. Now you will notice I didn't hook up the display board. I don't need it for full power up, and I just thought, well, we'll not take any chances, we'll just power up without it to start with. But I think I'm actually ready for that display board now. I've had it up to 240 volts and everything looked okay. Okay, and we're ready for power up. Again, this time I'm not going to bother winding the power supply up manually. I'm just got it set to 235 volts or something like that, and we'll just put power in. And yes, we've got something on the display there. Yes! And we've got something on the display. Wow! Let me hook up a voltage source. Right, I've got a voltage source hooked up off camera there. Now I noticed it did say calibration lost, but we knew that, so when I put in this voltage here into the DC input of the meter, it's not going to read right. I just wanted to see whether it was actually working. It would vary with the DC voltage input, so we'll give that a bash now. So we're all hooked up. I'm set to 10 volts, so let's put power in. It does take a calibration data lost. 10.1 volts. Let me put it down to 5 volts. The input's working. I can't believe it. Wow. So perhaps the only problem I've got right now could be I just need to recalibrate the meter. Wow. And as you can see, on the multimeters, my AC input's 247. Let me put that down a touch. 241 versus 225. Now let me just push the AC input down a little and let's see what the transformer primary does. And look at that, it stays pretty much stable, even though I've reduced the AC input by 20 odd volts. It only really dropped about 2 volts. Yep, I'm now coming down too far. Now the pre-regulator now is turned off completely, so it's probably at the minimum end now of that AC input. So it seems to start kicking in. Let's see, 238 volts. You saw it kick in there. It did take a few seconds for it to happen, but that'll be the integrator. As per my last video, the integrator does take a little bit of time to actually toggle that digital output on the pre-regulator. But that's looking great. Well, what's next? Well, actually, what I think I will do is build the boards back into their chassis. I can't see me having to work on the undersides of the boards to fix any further faults. Possibly just the top sides, and I can get to both of those boards from the chassis, either side of the chassis. So I think I will actually go ahead and reassemble the meter. Okay, here's the chassis. Let's reassemble it and then I'll come back. Okay, and that's it reassembled. As you can see, there's the analog board, the A to D, and everything's cabled up nicely. Transformers in. And the other side, the digital board, all cabled up. And the rear of the unit there. And the front panel. Now, I did actually have to use the donor chassis, believe it or not, because the posts on the back of the unit here are a smaller diameter on the donor chassis compared to the original chassis. So because I'm using the donor analog board and these tails here are soldered to the donor board, they wouldn't fit onto the posts on my original chassis, so I had to disassemble it again and then go and get the donor chassis assembled. But it's in perfect condition as well, there's no problem there whatsoever. But just nice to note those little differences there. I've still got to put in the hex nuts, etc. for some of the connectors, and I've still got to put in the big cover, the conductive cover there. I'll put that on later after I've powered up and after I've made sure it's all working okay. And there, of course, is all the components that I'd removed off the analog board for that voltage switching, etc. I find it quite funny actually that somebody someday might get a hold of this meter and maybe use it and open it up and go, what on earth's going on down here? But I find that a little bit funny, but that's just me. So let's power it up. Okay, here we go. One thing I should have done is maybe change out the fan on this unit here, because this is the donor chassis after all, and it is quite dusty, so I'll change out that fan later on. I suspect it's probably going to be a little bit noisy. And the fan's running there, and we've got power up. And the only error that's coming up there, if I saw it right, was just the calibration had been lost. Okay, it seems to be powering up okay. Let me put the analog cover on now. And there we go, certainly got a quieter fan now. Well, there's the Keithley 2001 with the case back on, and I think I'm ready to start doing some self-tests. There is a number of self-tests I can run on the front panel there to test out all the hardware, etc. And of course I've still got the recalibration to do. But I think that's enough for this series of videos actually. I'll not bore you with the calibration and the self-tests, but I have to say I have absolutely really enjoyed this repair. I wish I could get more of these. mammoth repairs on the workbench, rather than your normal just fix an odd component here or there. I really like getting my teeth into it. And I'll just finally put a shout out: if you have your own test equipment that's maybe faulty and you can't repair it or don't want to repair it and would like to donate it to the channel, individuals or companies alike, please get in touch. I would really love to get my teeth into more like this. Thanks for watching.